This is a lecture about the natural logarithm. It's kind of a more mysterious function than what we're used to. We do use it quite a bit, though, in mathematics. This is going to be a longer lecture than normal, and so I'm going to break it into two pieces. This is part one. So let's start. We're going to define something called L sub p. We're going to start at the p refers to a partition. Let p be the partition A is equal to x naught is less than dot 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 less than equal to xn equal b. And now define L sub p of AB to be equal to the sum from I equal n 1 to n of 1 over xi times xi minus xi minus 1. Okay, so what this is referring to, it's area under a curve, right? We have the curve y equal 1 over x, okay, and we are approximating it below by little rectangles. This is exactly the sort of thing we did when we were doing integrals, okay, back in Calc 1 when integrals were introduced. What I want you to note here is that LAP, this approximation of the area under the curve, on one hand it's bigger than, okay, B minus A times the shortest rectangle that's contained under them, but it's smaller than B minus A times the height of the largest rectangle that is under there. In fact, this, 1 over A height, it's on this end. This would be the big rectangle. It's definitely smaller than that, but it's definitely bigger than this one, which extends across the bottom. Okay. So what I have here with LPAB is an approximation of the area under the curve. To get the area under the curve, what we're going to do is we're going to take a least upper bound. We're going to define L of AB to be the least upper bound of the set of LP of AB, where P is a partition of AB. So we're going to just all possible ways we can chop that interval up into little segments, and then all the little ways that we can get rectangles underneath. We'll take the least upper bound of that set, and as we saw on the previous slide, it is bounded above, so this least upper bound exists. Okay, our first we're going to be using this L of AB to define natural log, but in preparation for that, what we're going to do is define some properties of this LAB. Okay, so our first one is if m is greater than 0, then LAB is equal to L of MA MB. So otherwise we multiply both of the endpoints of our interval by m. The area under the curve will remain the same. Okay. So the first thing we're going to do is show that LAB is less than or equal to LMA MB. We approach this by getting a contradiction. Okay. Suppose that LAB is actually bigger than LMA MB, and we'll get a contradiction from that. With this assumption, there is a partition, okay, P, again, usual notation, so that LMA MB is strictly less than LP of AB, which of course is less than or equal to L of AB. Now, given that partition, I'm going to define a new partition of a different interval, I'm going to just say take every point in P and multiply it by M. Okay, and so that gives us a partition of MA, MB. Okay, so this L sub P sub M of MA, MB, that's going to be equal to L of AB. Why? Well, we just write it down. LP sub M of MA, MB is equal to the sum of 1 over M sub x, mx minus mx minus 1. I can factor out the m in the numerator and cancel it with the m in the denominator, and that gives us exactly what LPA is. Okay, so it now follows that LMAB is less than or equal to LMP of MAMB, which contradicts the definition. Well, that by definition, L of MP has to be less than or equal to L of MA, MB. Okay. So since we get a contradiction, we are forced to assume that LAB is less than or equal to LMAMB. Okay, so now we're going to prove in the other direction. We're going to prove that LMAMB is less than or equal to L of AB. And we're going to be kind of tricky here. Note that if I take 1 over M, that's greater than 0, 2. From our previous result, we know that, okay, first of all, L of AB is equal to 1 over M times MA, 1 over M MB, and that by our previous result that this is greater than or equal to L of 1 over M. And so we got it. Okay, so we've got L of AB trapped between L, MA, MB and itself. Therefore, everything has to be equal.